Okay, so just a quick look at what we're covering today. So we're going to do a quick intro into Spectrum Centre for those of you that are new to us. Martin will then be looking at an overview of 452, the propagation mechanisms of that propagation model. He'll look specifically at the hydro-meteor-scatter feature of 452 and the implementation in general terms of 452 in Spectrum E. Like I said, at the end there will be an opportunity to have some questions and answers. Okay, so who are we and what do we do? Spectrum Centre are spectrum management specialists. With the unification of former offices from ATDI Group, we have offices in London, Washington and in Brazil. We offer a web-based solution called Spectrum E, which features 3 modules, one for technical analysis, remote monitoring and e-licenses. And these can be purchased as an overall solution or they can be purchased singularly. We also have a very, very flexible platform which can be modified to meet end user needs. Lastly, we do continue to offer our professional services in the form of consultancy. We offer a broad spectrum of services in terms of technology and market reach, whether that's from coexistence and interference studies to drive tests to identify not spots. As I said, the scope is broad. I'm going to hand over now to Martin, who's going to continue with the presentation. Thank you, Martin.
Thank you, Sarah, and good morning, good afternoon, good evening to all the attendees. My name is Martin Reyes, and I am a RF engineer with Spectrum Center located in the Washington, D.C. area, and I'm going to take over here and run through the rest of these slides that we have that deal with ITU-R P.452, and then we'll have a look at its implementation in Spectrum E, so our online web-hosted software. So first, a little bit about propagation models, why they're needed, what they're used for. So RF, standing for radio frequency propagation models, are used to predict path loss and power seed values from signals. And there's different ways of creating these propagation models. They might be curves fitted to measured data. They might be very statistical approaches. They can be very theoretical, or it can be a combination of everything. What's important to note about these propagation models is that they can be used for both wanted and unwanted signals. So typically your wanted signal is the signal by which you measure the performance of your system, whereas your unwanted signal tends to be your the interferer. And so that's for both wanted performance and unwanted interference events. So a little bit more on why propagation models are required. On the right-hand side of the screen here, you can see a band plan. And each one of those individual boxes represents a certain frequency range and the types of services that can be within that frequency range. And many times you'll see the overlap, 2 or 3 or even 4 different colors within a certain frequency range. While there is often a primary user for a frequency range, you might have secondary users. And even within the same system type, you might see interference between those different system types. So why are propagation models especially important in today's world? Well, again, you can see the amount of congestion that there is, but also since there's a ever-increasing demand for wireless broadband services. So we're talking 4G, 5G, and also this spectrum is quite valuable. Especially for larger countries with many users vying for the spectrum. Even several hundred megahertz of spectrum can be sold for millions of dollars or even billions of dollars. So the spectrum, not only is there a lot of contention for it, it is quite valuable. And once users have licenses for spectrum, they've put good money for them. They want to be protected. So propagation models like this can be used to model interference events. So now we move on to the propagation model at the center of today's discussion, and that's ITU-R P.452. Again, as you are all probably very familiar with, ITU is the International Telecommunications Union, R stands for recommendation, and P means that we're talking about the radio wave propagation series. And so that you have the entire name of this recommendation, it's the prediction procedure for the evaluation of interference between stations on the surface of the Earth at frequencies above about 0.1 gigahertz. So we're talking about frequencies over 100 megahertz. The reason why this propagation model doesn't deal with frequencies under 100 megahertz is that the characteristics of propagation below 100 megahertz are a bit more unique, and they require unique propagation models like those used for modeling AM radio and specifically ground wave and skywave propagation. So those lower frequencies behave a little bit more differently. And then once we start getting to the higher frequencies, you know, let's say above 50 gigahertz, where the ITU P452 kind of cuts off as, those propagation characteristics also start to vary a little bit. So what this means, you know, this from 100 megahertz to 50 gigahertz, it's a pretty broad range, and most of the RF systems that we're familiar with and use on a daily basis fall within this frequency range. And this can be used for, it says, stations on the surface of the Earth. So these can be broadcast services, terrestrial services, but also Earth space services, since there's transmitters and receivers that communicate with satellites and so on. So continuing on about 452, as I mentioned on a previous slide, propagation models are assembled from different elements. Some are very theoretical, some are very deterministic, some are very statistical, and so on. So P452 is kind of a combination. It has different elements to it. Some parts of it, as you'll see in the following slides, come from measured data. There's a statistical element to it, and there's a deterministic element as well. So something to immediately note is that the calculations for P452 assume time percentages within the range of 0.001% and 50%. So what that means is that a smaller time percentage means an event that is less likely to happen, an event that likely produces a greater amount of interference. So the smaller percentage we use, the more likely, or the more significant the interference event that there is. Also, you will see on the right-hand side of the screen, there are two images there. And these have to do with variation during the course of the year when it comes to rain. So the top image has to do with the rainfall rate. So you can kind of say the volume of rain you typically see, and the darker red areas on that map, as you can imagine around the equator, have more significant volumes of moisture, of precipitation, than the areas that get closer to the poles. And on the bottom right image, another thing that needs to be taken into account is the rain height. So, you know, at what altitudes is the rain most likely occurring? Where is it most voluminous? And so, you know, these are also ITU recommendations. So the rainfall rate is P837 and the rain height is P839. And of course, if the user has very specific local information, this information can be used in P452, but typically users are unable to obtain this information. So these ITU recommendations that cover the entire globe are often used instead. Then a bit more about some further inputs to the propagation model, and those include some atmospheric inputs. Three of the most important ones are these three parameters here: your delta n, your beta naught, and your n naught. So along with the information about rain rates and rain heights, these are the other parameters for the atmosphere that are required for the various propagation mechanisms. And there are 6 propagation mechanisms, as we'll see on the following slide. So the refractive index, or the delta N, also the average radiorefractive index lapse rate through the lowest 1 kilometer of the atmosphere. And the refractive index is what allows radio waves to bend in the Earth's atmosphere towards the ground, leading to the use of the K factor in propagation characteristics, and also leading to the fact that there's a difference between optical line of sight and radio line of sight. Radio line of sight tends to be further than optical line of sight. So if you can see a point on the horizon, well, if you send a radio wave, an RF signal in that direction, it will be able to go further than where you can see. The atmospheric conditions, they vary greatly, since the lower altitudes of the Earth's surface are the most important and are the most relevant for us for these calculations. So you can see that these parameters are for sea level, the first 100 meters and up to 1 kilometer from the Earth's surface. And they generally, these atmospheric inputs add a further amount of additional losses when propagation losses are being calculated. As I just mentioned, there are 6 propagation mechanisms that are computed in this one propagation model. So, like any modern propagation model, it's not a simple equation that's used. It's a whole number of equations and a whole different way, whole set of ways that a signal can travel. And we're going to have a look at each of these propagation mechanisms individually. And those are line of sight, diffraction, tropospheric scatter, surface ducting, elevated layer, reflection and refraction, hydrometeor-scatter. And finally, one other loss that's not necessarily a propagation mechanism, but it is a loss that needs to be covered as well, is clutter losses. So most times, and many times, your receiver and sometimes even your transmitter are located within clutter. You can say within a forest, under a canopy of trees, in an urban area, being shadowed by buildings and so on. So there's an additional amount of losses that need to be considered, and these are the clutter losses, and we'll have a brief look at those as well at the end of this presentation. So the first propagation mechanism is probably the most well-known one. It's highlighted by that red rectangle in the image on the right-hand side, and that is line of sight. So if in RF terms you have line of sight, if you can see, if you have a direct path between your transmitter and receiver, that is line of sight propagation. It's a clear propagation in free space with no obstructions in any part of the primary path. And this propagation mechanism uses the classic free space path loss equation, but also considers, this free space path loss equation is the classic one that considers the frequency at which the system is operating at, and also the distance between your transmitter and receiver, but it also adds a smaller additional loss factor, which is the atmospheric losses. And of course, as you probably well know, lower frequencies have lower losses, higher frequencies have higher losses. The second propagation mechanism that is also computed in P452 is diffraction. And diffraction refers to non-line of sight or beyond the horizon propagation, where the transmitter and receiver cannot see each other in RF terms. So in the image there, it appears that there is a mountain or a hill or something like that, and the transmitter and the receiver are unable to communicate by a direct path. There's only a path that is diffracted. So the diffraction methodology, as it is calculated in P452, it must be sufficiently robust to cover a diffraction over smoother, discrete obstacles and irregular terrain. So there's numerous ways that the diffraction is calculated, and this combination of these calculation mechanisms, this combination of the Boolington construction and spherical Earth diffraction yields what is called the Delta-Boolington method that is used for diffraction calculation overall. And when you have diffracted paths, similar to line of sight propagation, where higher frequencies encounter higher losses and lower frequencies have lesser losses, diffraction is similar. When a lower frequency signal is diffracted over an obstacle, there is less loss than there is for a higher frequency signal. Moving on to the third propagation mechanism, this is troposcatter, and it mainly pertains to UHF frequencies, which are from 300 megahertz up to 3 gigahertz, and SHF frequencies from 3 gigahertz to 30 gigahertz. So that's the meat of the frequency range where most modern communications occur, and thus are the frequencies that fit right within the P452 scope. As you can see in the image there, the scattered energy is not necessarily perfectly directional, as it is based on the characteristics on the Earth's troposphere, which is part of the Earth's atmosphere up to about 6 to 10 kilometers in altitude from the Earth's surface. So what's happening here is that your RF signal, your RF energy, is being randomly scattered by the upper layers of this Earth's troposphere. So those 6 to 10 kilometers above the surface of the Earth, the energy is hitting this level and then being scattered in all directions, actually. So there are those three arrows in that image specifically pointing to our receiver on the right-hand side of the image. So those are the rays we would be most interested in, but that scatter doesn't actually happen in just that direction. It can be scattered in many other directions as well. And this is mainly relevant for longer communication path. So we're talking at distances of 100 to 150 kilometers and further. Continuing on now, we're at our fourth propagation mechanism, for which there is a specific set of equations in P452, and they're calculated each time that the propagation model is run. And these are a little bit more irregular than the first three that were calculated. So surface ducting now, and that's caused when an RF signal is trapped in a duct. You can kind of say it's a sort of tunnel between the Earth's surface and the layers in the atmosphere where there are sharp changes in temperature or water vapor concentration. So as you go up in altitude from the Earth's surface, there are certain bands where there's a sudden rise in the temperature, or suddenly the temperature is lower, or you go from very dry altitudes and suddenly there's a band which has a lot of moisture in it. And the surface ducts are kind of these created by these layers of very sharp changes in the water vapor concentration and in temperature. And they help radio signals to get trapped between the Earth's surface and these layers. And you can kind of see in the image, they kind of bounce and continue to propagate over longer distances. And this is especially prevalent in areas where there is a higher water content. So we're talking about flat coastal areas or over water. So in many cases, this could go lead to beyond the horizon propagation, and that can be sometimes caused by surface ducting. Continuing on, now we're on the fifth propagation mechanism, and that's elevated layer reflection and refraction. So now we're talking about the Earth's atmosphere, but at higher altitudes. So previously for the troposcatter, we were looking at up to 6 to 10 kilometers from the Earth's surface. Now we're looking at layers above that. And like surface ducts, the elevated layer reflection and refraction is caused by sudden changes in the characteristics of the atmosphere. And this can lead to propagation over very long distances. We're talking hundreds of kilometers. And for those that were on the webinar last month, this might sound familiar to the skywave propagation that was covered at that point, where skywave is one of the main propagation mechanisms for high frequency HF systems that are designed to quote unquote bounce their signals from the Earth's ionosphere. So this elevated layer reflection and refraction is in a way similar to that. It's not the exact same thing, but it is a similar propagation mechanism. And of course, this is most prevalent and used for lower frequencies, as often higher frequencies are more likely to pierce through the ionosphere and the other layers of the Earth's atmosphere instead of being reflected or refracted back down to the Earth's surface. And finally, we reach the sixth propagation mechanism, the one that we're going to spend a little bit more time on, and that's a little bit more unique, and that is the one of hydrometeor-scatter. So since it is a little difficult to quantify, it is not exactly found in many propagation models. And what hydrometeor-scatter is, it's the energy that's scattered from volumes of moist air in the Earth's atmosphere. So in the image on the right-hand side, that is represented by a rain cloud. So the cloud itself, which contains moisture, and then the rain or snow that falls from the cloud are these, those are considered those hydrometeors. Those are the concentrations of higher density water vapor and just water content overall. And when an RF signal impacts upon these volumes of increased water vapor concentration, you end up with scattering of energy. So the hydrometeor-scatter can actually occur pretty much anywhere, but is most likely to occur where the main and side lobes of directional antennas overlap. That's not to say that it only is relevant for highly directional antenna patterns, but it can also be taken into account in omnidirectional antenna patterns. So a little bit more about this this phenomena, this hydrometeor-scatter. So it doesn't exactly exist in a vacuum. It's not a brand new thing. It has precedents. Hydrometeor-scatter calculations are in P452 is descendant from the method of COS210, also called the influence of the atmosphere on interference between radio communication systems at frequencies above 1 gigahertz, which itself is based on previous CCIR reports, the numbers of which you can see on the slide there. And when we were implementing the hydrometeor-scatter methodology into our tool, we use COS231 kind of as a baseline to verify the functionality of the propagation model, and specifically hydrometeor-scatter by itself. And the report about this, the baselining procedures and notes, are available as handouts, and will likely be emailed to you after the conclusion of the webinar. So since this methodology is computationally intensive, early versions sought to simplify certain aspects of the computation. So those earlier CCIR reports and the COS210, slightly simpler computation methodologies. And you will see this in the upcoming slides when we look at the various volumes that need to be computed, the various rays and angles, and so on. There is a lot of computation that needs to take place. And let's see, let's continue to the next slide. So why is hydrometeor-scatter even relevant? Well, in most cases, it's not a very significant contributor in propagation analysis, but there are certain events where it does need to be taken into account. So on this slide here, you can see there are two paths that are being shown. And both of these paths are non-line of sight signal paths. One is through hydrometeor-scatter, and the other one is through diffraction. And we're considering that the transmitter and receiver, in this case, both have highly directional antenna patterns. So in most cases, the diffracted signal strength will be stronger. It'll be superior to that of the hydrometeor signal strength. Yet, you know, if in the situation, if you have the transmitting and receiving antenna patterns pointing to each other or in the same general direction, and the diffraction attenuation is high, there might be enough energy that is scattered by the hydrometeor to to create a stronger signal, a stronger interfering signal at the receiver station than there would be from the signal that is diffracted. And as I mentioned, this is typically most important for very directional antennas, but it can also happen in their side lobes or for particularly powerful omnidirectional antennas as well. And the reason this is quite relevant is, actually another aspect that has to be taken into account is that not all directional antennas on the Earth's surface are fixed. One must not forget about the satellite tracking antennas, such as those used for tracking non-geostationary satellites, since their antenna pointing is frequently changing as they track satellites across the Earth's surface. So not all hydrometeor scatter calculations happen with the antennas pointing in the same exact direction. So now a bit more about how it is computed, antenna patterns, and things that need to be taken into account. So just like any other propagation calculation, it is best to know the exact antenna pattern for the systems involved for both the transmitter and receiver. But when this is not possible, when the user does not have access to these antenna patterns, generalized antenna patterns can be assumed. And these antenna patterns, again, are recommendations from the ITU, such as F699 and F1245, and of course there are other constructs that will create generalized antenna patterns that can be assumed. So again, for the most precise analysis, the exact antenna pattern is desirable, but a generalized antenna pattern can also be used, since in many cases the generalized antenna patterns are calculated using the frequency and antenna gain. So as long as those two parameters are known, typically a generalized antenna pattern can be constructed. And it's also important to remember that not only is main beam to main beam coupling possible, but many times side lobes are only 20 to 30 dB lower than the main beam. So side beam coupling should be considered as well. So the simplified way of talking about how hydrometeor-scatter is computed is to think of the bistatic radar equation on which hydrometeor-scatter is actually based upon. So kind of to create an analogy here, while we are most used to seeing monostatic radars, so those are the radars, the antenna typically painted red, orange, that are rotating on towers near airports, those are monostatic radars, and those function somewhat differently. So a monostatic radar transmits and receives a signal from the same point, from the same antenna, and a bistatic radar is different in that it uses two separate geographically dispersed or far away from each other antennas. So you have a transmitting antenna and specifically a receiving antenna. And in the two diagrams on the right-hand side, you can see, again, we're continuing with this analogy, with this aircraft tracking analogy, in that your transmitter transmits the signal. It is scattered by the target. In this case, in the images, both are airborne aircraft. And then there is a receiver location which receives that scattered energy. So this is analogous to how hydrometeor-scatter works and how it is calculated. And many of the parameters in the bistatic radar equation are also relevant for hydrometeor-scatter, especially considering the distances, the powers, the gains, and the frequency characteristics. So the main difference between how hydrometeor-scatter is calculated and the bistatic radar equation is what's called, in the bistatic radar equation, the radar cross-section, or how large an object appears to the radar. So instead of us being interested in how large this aircraft or how large this target appears to the radar system, we're more interested in what the size of the hydrometeor volume is. When you have this denser concentration of rain or just moisture in the atmosphere, how dense is it, at what altitudes is it, and so on. So instead of wanting to know, how large an object appears, analogously, we're looking at how large the volume it is, how dense it is, how far above the about the Earth's surface it is as well. And continuing on, as was mentioned previously, hydrometeor-scatter doesn't necessarily occur in a direct path between two stations. It can happen outside of that path. It can happen pretty much anywhere. So this slide is designed to help visualize the geometry at play in hydrometeor-scatter. Looking on the image on the left-hand side, and these figures are both taken from the P452 calculation methodology, you can see the direct line of sight, or the direct path between stations 1 and stations 2, represented by array R12. So that's that red horizontal line at the bottom of the image. But our hydrometeor volume, the volume of rain, or the volume of increased water vapor concentration, is not on this direct path. It's at an angle. It's at an outside angle from both of these stations. So we're not calculating in the middle of these two stations. We're calculating at a different azimuth from each of them. So as explored earlier, the rain heights vary and atmospheric conditions vary, making it necessary to explore different locations for this cylinder and different heights in the cylinder as well. And then you'll see that there are two vectors there, vector v10 and vector v20, and these are the antenna pointing directions. And you can also see that they do not exactly overlap in this volume of water vapor concentration. There can be a difference in their pointings, and so they don't necessarily have to overlap. But as long as it's somewhere within this hydrometeor, as long as it's somewhere within this volume of increased water vapor concentration, it is possible that the signal being sent out by one station, let's say station 2 in this case, is scattered within this volume, and enough energy is scattered in this volume to be received at station 1, causing interference to that station. And also a quick word about the diagram on the right-hand side of the page as well. And what that denotes is that there are different volumes within that cylinder of calculation that need to be calculated, and they have to do with rain height. So the volume of moisture, the water vapor concentration in a cloud, in a column of rain, is going to vary at different altitudes above the Earth's surface. So there's different amounts of water present at those different altitudes. So what P452 does is it separates it into 3 different volumes. There's lower volume, middle volume, and upper volume. Typically, when it's raining, the lower volume has the greatest amount of water vapor concentration. If it's just particularly cloudy, maybe the middle volume has a higher volume of concentration. And this is all something that's taken into account in P452 and has to do with those ITU recommendations stated previously, P837 and P839, that determine rain rate and rain heights. And one more word about that diagram on the right-hand side is you can see there are certain areas that are highlighted in red. So the propagation path that's being calculated is not necessarily fully in one volume. It might partially be in the lower volume, yet the intersection point or the refraction point, the scattering point, might be at a higher volume. So this makes the implementation of this methodology that much more difficult to compute, since in one, when you're looking at one specific point in this volume, you have to consider the path. So there's part of the path that is outside of your hydrometeor. It's outside of this cylinder of increased water vapor concentration. then there's a part that's within the column, but maybe the volume of water, the water vapor concentration is lower, and the actual scattering point is at an altitude where the water vapor concentration is higher. And what happens in the calculation overall is that for every point within this volume, it is evaluated for the scattering and how much energy it can contribute to the power received at a receiver. So instead of just calculating one path profile and seeing how much path loss there is using the 6 different propagation loss mechanisms, instead you are looking at a volume and you're calculating the path loss for the transmitted signal to make its way into that volume to be scattered at each point in that volume, and from each point the path loss from there to the receiving station. So you can imagine this is a very large amount of computations, and one of the reasons why the previous versions of Hydrometeor-scatter involved many simplifications, and also why it is not necessarily a part of many propagation models, also because it is often not a very high contributor to propagation characteristics. So a little bit more about P452, and we have these last 2 slides which cover clutter or land use. So what that refers to is the fact that the Earth is not bare. Its terrain data sets are very easily available. There's many of them, differing resolutions and accuracies. But clutter, what's actually covering the surface of the Earth, is a little harder to qualify and quantify. But it can be a very significant element in any sort of propagation analysis, since in most cases, users, and particularly users using broadband devices, which is very relevant to any generation of mobile device, are located below the height of clutter that surrounds them. So if we're talking about trees, users are typically lower, are shorter than trees. They're located in buildings, they're located behind buildings, and so on. So it is, for the utmost accuracy, clutter should be included and should be calculated as well. So as implemented in P452, the shielding losses, or the clutter losses, typically are around 20 decibels at frequencies above about 900 megahertz, and go down to about 5 dB at around 100 megahertz. And these shielding losses, these clutter losses, can be added at either or both ends of a propagation path. And now, as with the antenna patterns, it is best to have the most accurate information possible, but it is not always possible to obtain this sort of information. So recommendations and standards can be used, and P452 uses nominal clutter categories as defined by the ITU, in this case P1058, and on the right-hand side we can see these nominal clutter classes and also their heights and distances. So when the surface of the Earth is classified, every point on the Earth is assigned one of these clutter classes. And by being assigned one of these classes or categories, a clutter height is assigned to that point on the Earth's surface as well. And then there's also a nominal distance. The nominal distance is typically how far away is the user or the receiver antenna from this type of clutter. So typically, when you're located in a forest, how close are you to the nearest tree, and so on, and that is used as part of the clutter calculation or clutter loss methodology. One final word on clutter calculations is that P452 accounts for both line of sight propagation to a nominal clutter location, but also if the path is shielded behind an obstacle, when there is diffraction in the path as well. This can be seen in the image on the right. There is a gray line which goes directly from the transmitter. It goes into an urban area, and within that urban area where that asterisk is located, that energy is diffracted or makes its way through the clutter that there is and is received at the receiver location. So that's one way of the RF signal making its way from a transmitter or receiver through clutter. But it's also possible that the signal is diffracted along the way first before even reaching the clutter, and this is the that site shielding obstacle that is located in its path. And again, the clutter information is not necessarily easy to obtain, and the higher the resolution, the better it is, the more accurate the outcome will be. But there are standards and recommendations that can be used for the calculation of clutter losses as well. So now that we've had a look at P452 as a propagation model, as a document, and the various propagation mechanisms that are present in it, we're going to switch over to Spectrum Center's Spectrum E web tool, and we're going to have a look at how the propagation model, how it appears when it's being used. So let's switch to a network here. I've previously created a network with 3 stations, and just I guess a brief couple of words about Spectrum E and application. It's a web-hosted application. Users obtain subscriptions and then are provided with a username and password to access the system. There is a worldwide data set for map and cartographic data, full 360 degrees, the entire globe. There's different ways of viewing this cartographic and terrain information. Users then able to create different types of stations, whether they're point-to-point stations, whether they're Earth satellite receivers, whether they're cell phone towers, and so on, and are then able to run their point-to-point, point-to-area, and also interference analyses here. So I'm going to show you some of the functionality for the point-to-point and also point-to-area abilities of Spectrum E using the P452 propagation model. As you can see here, now we're in the United States, in the state of Colorado. We have 3 stations located on the map, and now we're going to run some path profile analysis between them. For example, if we take these 2 stations, on the left-hand side of here of Spectrum E, we have the different functions that are available, and this list is not exhaustive. It's just an example of the functionality that's available. And we're going to go to the P452 path profile. In this path profile, different information is being shown to us. The red line shows us free space loss. If there's no diffraction, no clutter, nothing like that. So that would be an ideal line of sight case. And when a propagation model is taken into account and not just free space loss, of course, you would imagine there to be more loss than just free space. And in this case, you can see that this path has multiple diffraction points from the transmitting location to the receiver. So we have further lines here. We have an orange line and a green line, and those tell us further information about the path loss along this path. So we're seeing in the orange, that is the propagation model. So P452 by itself, the amount of losses calculated along the path. And then if we take into account clutter losses as well, that adds this green line to it. So typically when clutter is calculated too, there is further losses than just those calculated by the 6 propagation mechanisms in P452. Along the bottom of the screen, you can see here we have the different clutter classes are being displayed as we're moving along the path. And also at the bottom of the screen, we have information about the distance, the locations of the stations, some of their parameters, and then the amount of loss calculated. So our free space loss in this case at the receiver point, about 112 decibels. If we look at the propagation model, P452, that adds approximately 36 more dB attenuation. And if we add clutter loss to that as well, that's another approximately 16 dB of loss on top of that. And SpectraMeet here in the path profile screen allows the user to then further configure their analysis. These gears in the top right-hand corner allow the user to, in real time, change the heights of the transmit-receive antennas, to change the propagation model. And right now you can see that we're using P452 to include or not include clutter heights in the calculation, and also to change the time percentages. So here we're looking at 50% of the time. This can be lowered this can be lowered to a different time percentage, which would change the results that we're seeing on the map. Also to change from average to worst months performance, and if there's different clutter, we can turn the clutter off. We can choose if it's only at the receiver, and there's also a high resolution clutter option. So that's a brief look at the path profile screen using the ITU-R propagation model P452. Now we're going to have a look at a little bit of point to area coverage. So I created a network for that in a different part of the world. So if we have a look here, we're looking at 6 stations. I'm going to jump to where those stations are located. In this case, we're looking at the Netherlands. We have a grouping of 6 stations here. And if I jump back to the network page, there are my 6 stations with all their parameters. And I have the ability for all of them to run the P452 path loss calculation. And this calculation is fairly quick. For these 6 stations, it would not take any more than a minute or two to calculate the amount of path loss up to a distance of 100 kilometers away from them. But just to save time here, we're running a little low on time. I'm not going to run those path loss matrices, the calculation for them in real time. Instead, I'm going to go back to the map, and I'm going to pull up a coverage that was created previously. And the way that this coverage is being displayed is kind of in a step palette. So each of those colors represents a different power received level. And in this case, this is a composite coverage. So it's the highest signal strength from any one station is the power received value at that point on the map that is receiving precedence and is being shown. And if the cursor at the center of the screen there, if it's moved around, you can look at the bottom right-hand corner of the screen. Might be a little hard for you to see since it appears quite small. So I don't know how well it's appearing on the webinar, what the resolution is. But in that bottom right-hand corner, you have the coordinates of that center point where those hash marks are, the elevation of the terrain at that point, but also the power received value for the prediction that is being shown on the map. So again, this prediction was generated using the recommendation P452. And with regards to propagation models, one last slide to show you, and that's just to mention that Spectrum Center's SpectraMe tool is, it's a propagation and interference simulation and spectrum licensing software tool, and we have an ever-growing portfolio of propagation models. So today we had a look at P452. Last month we had a look at skywave and ground wave propagation. But just quickly like to mention that we also have the NTIA irregular terrain model, also known as Longley-Rice, implemented, especially for our US users. There's also Ukamura-Hada-Davidson, more commonly used for mobile simulations. We have, and then we have a whole number of other ITU recommendations, which, for some of you, those numbers will mean something. For others, those will be just numbers. But in that list are further propagation models from the ITU that are implemented and can be used in the Spectrum-E tool. And now I revert control back to Sarah, see if there's any questions or any final words.
Thanks, Martin. That's great. Okay, so we've had a couple of questions coming in. If you have any questions, please use the question toolbar or put your hand up and I'll be able to unmute you. You can talk directly to Martin. Okay, first question refers to the scope of the bands for the application of P452. What about the 80 gigahertz band? E-band it's referred to in the UK and Ireland.
80 gigahertz band. So as is kind of in the defined for P452, it's typically meant to go up to 50 gigahertz. I don't see any reason why not to use it as a higher frequency, but I would assume there are other propagation models specifically for that frequency range that might be a better match, just based on the parameters that are called out for P452.
Okay, that's lovely. Thank you for that, Martin. I hope that answers your question, Kieran. What are the standards used to calculate clutter? So this is on the mapping side of it. What are the standards used to calculate the clutter?
So what we have implemented in Spectrum-E is a worldwide clutter classes that are derived from satellite imagery and various other remote sensing techniques of the entire planet, since we constantly have non-geostationary satellites that are revolving around the Earth and getting this information. And then there are various body, whether they're educational institutions, governments, and whatnot, that then define ways of computing or number crunching this information and creating these clutter classes. So the clutter classes are defined by the ITU, or in P1058. Those are the clutter categories, and our clutter heights are taken from that. But the actual clutter coverage of the entire world is taken from different sources available, or that are typically publicly available. And if you'd like further information about where the specific clutter comes from, what data sets, please feel free to contact us, and we can follow up with you and provide you with more specific information, especially based on what part of the world you're located in.
That's lovely. Thank you. I hope that helps, Philip. Okay, so just touching on that again. So can customized clutter be used instead of the standard Spectrum-E clutter?
So custom clutter can be used. It depends on what sort of access the user has to Spectrum-E. Since one of the new additions we currently have is that users can use their own, are able to use their own custom terrain. So there is there's a worldwide terrain database and a worldwide clutter database. And for their own personal uses, let's say you have a surface mining operation and you're expecting there to be changes in in your terrain, in your clutter at a certain point, on the Earth's surface, going years into the future, or you want to calculate for years in the past. Users, if they have this functionality exposed to them, if this is something they're interested in working with, are able to upload these data sets and work with these custom data sets that they import into the tool.
That's lovely. I hope that answers your question, Nick. Okay, and one final question just on clutter. Please do keep them coming. We've got several more minutes that we're running. We're happy to take your questions. What is the clutter resolution used in the US and Canada? So that's Ibrahim.
So with regards to the clutter resolutions, I am right now blanking. I believe it's 30 or 90 meter resolution. It might be 30 meters, but that's something we might have to get back to you on with the precise answer. I do believe it's 30 meters, and actually for the US, a 10 meter resolution database is also available. So in the US, the high resolution terrain database is 10 meters. Otherwise, I believe for the worldwide, 30 meters, and in worst case, absolute worst case, it's a 90-meter resolution clutter database.
Okay, that's super. I hope that helps, Ibrahim. Okay, as we're waiting for a couple more questions to come in, just some follow-up from today's event. You will be sent a link for a survey that will give us some feedback on today's event. Your feedback's important. It helps us develop future events and make sure that we're positioning and targeting our webinars on the right subjects. I'll also be sending you a follow-up email. The follow-up email will include the white paper, which is authored by Martin himself. The recording link from today's event, please share with any colleagues who are unable to attend, and a registration link for our user group that we're holding in January. Okay, we've got a couple more questions that have come in, specifically about modulations. Are there specific modulations that this model works best for?
So with regards to these propagation models and modulations, propagation models typically don't take into account what modulation is being used unless it's a very specific propagation model that is designed for a specific system for a specific signal type. So modulations are typically have more to do with the performance of your receiver. So what sort of power do you need to receive at your receiver to pull off a certain modulation? So if it's a higher order modulation, the more complicated one, typically you need to have a higher signal receive value or a wider bandwidth, something like that. So a lot of times you can say that the propagation models are modulation agnostic, and P452 is one such propagation model. It doesn't really take into account the modulation that you're using. It's more so based on what your system type is and the performance of your receiver.
That's lovely. Thank you for that, Stephen. I hope that answers your questions. Okay. In the absence of any further questions, I'd just like to say, Martin, thank you so much for taking today's event. Thank you, everyone, for joining us today. Please, like I say, look out for the follow-up email. Registration for January's user group meeting on the 9th of January, and a link for the recording from today. And one last plea, the survey. If you do take 2 minutes of your time just to complete that, I'd be most grateful. Thank you, Martin. Thank you, everyone else. Have a great day.